Hello everyone, my name is Shoaib Mahmood and my colleague's name is Mir Faisal Tarif. Our presentation topic is design and simulation of a hybrid power system for Norman Bay. Now our project overview. Norman Bay is a small remote community in Labrador and that currently relies entirely on a diesel generator. This method is both environmentally harmful and financially unstable. Our project is to design a hybrid renewable energy system using solar, wind and battery storage to reduce diesel dependence, improve reliability and lower emission. Project objective. Our goals are clear: reduce diesel fuel consumption and the associated greenhouse gas emission, utilize local renewable resources like wind and solar, and simulate and optimizing the system using Homer Pro and MATLAB Simulink. We have chosen this site because Norman Bay is a small town of just 19 residents on the southeast Labrador coast and is accessible only by sea or air. The daily average load is approximately 420 kilowatt hour with a peak 62.44 kilowatt. Currently, power is entirely diesel based, which is both costly and environmentally taxing. For this reason, we chose this area to implement renewable energy sources like wind turbine and solar PV system. Literature overview. Several similar studies have been conducted for other remote Labrador communities like Blacktickle and Battle Harbour. These studies show that a hybrid system significantly reduces fuel use and emission. For example, Blacktickle achieved over 92% renewable penetration using Homer Pro. Design and methodology. Our approach includes assessing the local solar and wind resource, analyzing the community load, selecting appropriate components like PV panels, wind turbines, diesel generators. Actually, the diesel generator is now existing, inverters and batteries, and running optimizing and sensitivity analysis using Homer Pro and MATLAB Simulink. We have a proposed system configuration our system configuration our proposed system configuration includes 20 kilowatt of solar PV, 10 kilowatt of wind power, 50 kilowatt diesel generator which is already existing, and 72 batteries. An inverter is included for AC loads. This setup is designed for reliability and maximizing renewable energy share. For load profile, this graph shows the load profile of Norman Bay. As mentioned earlier, the average daily load 420 kilowatt with peak demand reaching 62.44 kilowatt. The load factor is 0.28, indicating variability throughout the day and year. For power production, our simulation showed that the hybrid system would produce around 21,785 kilowatt a year, which is around 12% of total generation from PV, and from wind turbine we got 76,189 kilowatt per year, which is around 41.8%, and the rest of the power we generate from diesel source, which is almost 46.3%. And our AC primary load is around 153,299 kilowatt hour, which is and we have some excess energy which is around 15%. Homer optimizing result. Our best configuration as determined by Homer Pro resulted in a levelized cost of electricity of $0.5541 per kilowatt hour. This system achieved a renewable fraction of about 62% and a 70% reduction in emission compared to by diesel only system. Environmental and economic impact. This system would significantly reduce greenhouse gas emission and lead to long-term fuel saving. We calculate a payback period of approximately 7.5 years, making it both environmentally and economically viable. For cash summary, compare current system and proposed hybrid power system over 25 years. The total system cost is around $1.09 million. The diesel generator contribute the most of this cost due to the fuel and maintenance. However, the renewable component, while initially costly, provide a long-term savings. Here we present the dynamic simulation model developed in MATLAB Simulink. It integrates all the system components and control logic, allowing us to simulate real-time behavior and ensure optimal power flow. For diesel generator output from the MATLAB Simulink, the graph shows the three-phase AC output of the diesel generator. Its output varies based on the load demand. Peak indicate high consumption and dips significantly reduce use, highlighting the generator's role in the system stability and energy balance. The generator acts as a backup when solar and wind aren't sufficient. The wind turbine provides a stable three-phase voltage. Power generation fluctuates depends on the wind speed, contributing significant during winter months when the solar irradiance is low. Wind turbines output in terms of voltage, current, and power variation over time. The top graphs illustrate the three-phase voltage waveform, maintaining stability during operation. The middle graph depicts a current variation, which show a sharp decline at a certain point, indicate reduced wind energy availability. The bottom graph represents power generation, which initially increase peaks and then gradually decrease, reflecting wind speed fluctuation. In this scenario, the existing diesel generator has a 50 kilowatt capacity, while the system average power consumption is 17.5 kilowatt per hour. Since the wind turbine produce variable power, it helps reduce diesel generator use when wind conditions are favorable. The reduced power consumption by wind turbine contribute to fuel saving and improve efficiency, demonstrating the hybrid system ability to integrate renewable energy sources effectively.
Thank you, Shoaib Mahmood. My name is Mir Faisal Tarif, and rest of the presentation portion is be delivered by me. In my portions, uh, here we can see the PV output analysis. The graph here shows how the solar irradiation and consequently power output changes over the time. Initially, the irradiation is flat, and so is the power output. As sunlight increases during the day, the PV system starts generating more electricity. We observe a gradual rise in the power output, followed by a temporary dip, probably due to cloud cover or system adjustments, and then it stabilizes again. However, it is important to notice that since our diesel generator has a capacity of 50 kilowatt, the PV system is reliability small is comparison. This means that while solar energy helps reduce fuel use, it can't fully meet the peak energy demands, and the diesel generator still need to support the system during high load period. So this slide focus on the overall system's ability to maintain power and voltage stability. On average, the load power remains around 17.5 kilowatt, which aligns well with our expected values based on community uses. More importantly, the voltage stays well regulated across the system. The stability proves that the hybrid system design is not only effective in the term of power generation, but also reliable in ensuring high quality, uninterrupted electricity for the people of Norman Bay. Here we look at battery behavior through its state of charge or SOC. At the start of simulation, we see a high initial discharge which is expected as the system begins powering the load over time, and the SOC gradually decrease depending on how much renewable energy is available to recharge the batteries. This show how crucial batteries are in balancing short-term fluctuation when wind or solar production suddenly drops, like when a cloud passes. The batteries step in immediately to smooth out the gap before the diesel generator kicks in. So the next slide is control system design. Our system includes a control logic design and tested using MATLAB Simulink. This control system ensures three major functions: load balancing, source polarization, and power flow optimization. It constantly evaluate the available resource and automatically choose the most efficient combination, favoring solar and wind first, then using the battery, and finally the diesel generator if needed. The intelligent control is what makes the hybrid system efficient and renewable even with fluctuating energy inputs. Now let's zoom in on the wind turbine controller. This controller dynamically adjusts the blade pitch angle based on wind speed to maintain an optimal TP speed ratio. Doing so helps the turbine extract the maximum possible energy from the wind. It also prevents overspeeding, which could otherwise damage the turbine. The graph in the slide shows how the power coefficient CP varies with both pitch angle and wind speed, guiding the control system in making adjustment in real time. The next slide is PV controller design. So the PV controller has three main jobs. First, it implements maximum power point tracking MPPT to ensure that we extract as much power as possible from the solar panels at any given moment. Second, it stabilizes the DC link voltage, which is important for smooth operation. Finally, it synchronizes with the grid-tied inverter to inject clean, reliable power into the system. Overall, the PV controller ensures a stable and efficient solar energy contribution with minimal oscillations. So the protection system overview, like no system is complete without safety features, and our protection system is designed to ensure safety, stability, and reliability. It continuously monitors for faults like overcurrent, overvoltage, undervoltage, and overtemperature. When something abnormal is detected, the system automatically isolated the affected components to prevent further damage or service interruption. In remote communities like Norman Bay, having such an automatic protection mechanism is especially important as technical support may not be immediately available. The first key challenge is seasonal variability. Solar drops in winter and wind can be inconstant. Secondly, the system requires regular maintenance and technical skills which can be difficult in remote area. Lastly, there are a high upfront cost, especially for batteries, through long-term savings help balance this over time. Conclusion: our hybrid system combining solar, wind, batteries, and diesel meets the community's energy needs while cutting emission by 70% and achieving over 60% renewable penetration. This is not only technical feasibility but also economically and environmentally beneficial, and it can be applied to other remote communities as well. Future scope: the future improvement includes adding micro hydro or tidal power for more reliability. We can also enhance efficiency with smart predictive controls and simplify upkeep through remote monitoring and diagnosis. Thank you for listening.